So today, you guys, we're going to learn two things. Determine whether or not a statistic is unbiased or biased of a population parameter, and describe the relationship between the sample size and the variability of a statistic. Okay? Those are only two things. So, first thing we want to ask ourselves is how trustworthy is a statistic as an estimate of a parameter? So if we just do a sample, how trustworthy is that going to be? So to answer this, we can look at the shape, the center, and the spread of the sampling distribution. So let's start by looking at the center. We're going to talk about biased and unbiased. So if we're talking about the red chips, right, we passed the bag around. There was 100 red chips, 100 blue chips. Everybody took a sample size of 20 when we did this. And you guys then put all your little dots on the graph, right? And so this right here was like a 500 of them or something. So 500 simple random samples. So we noted earlier that the center of the distribution is very close to 0.5. Remember, we got 0.499 or something like that. And in fact, if we took all possible samples, so every single possible sample from the bag, and calculated for every single sample the proportion, we would get a center of exactly 0.5 for all of our little p-hats, right? So we talked about that. So if the center matches the true proportion, then it's called an unbiased estimator. If you get the same thing. So a statistic used to estimate a parameter is an unbiased estimator if the mean of its sampling distribution is equal to the value of the parameter being estimated. So with the red chips example, it would be an unbiased estimator because we would get a center of 0.5 if we had every single possible sample of 20. They would all center around 0.5. Which is the true proportion in the bag. It may not always be exactly perfect, you guys. So if it's close, really close, we still consider it unbiased. What it's going to look like if it's biased, which you're going to have to be able to like tell, might look something like this, where maybe the center of our sampling distribution is 0.6 instead of 0.5, right? If you can tell the graph looks off from what the true center is, then we call that a biased estimator. Another side note, when we did chapter 4, we talked about biased and unbiased, right? When we had like a convenience sample, and that was biased. This is assuming that your samples are not biased, okay? So assuming simple random samples are all not biased as far as how you conducted the survey. As long as your centers are the same, you can say it's unbiased. If your centers are not the same, you would say it is a biased estimator. Yeah.
So it's biased even if the surveys produced perfectly? It still can use the biased estimator?
Yes. Yes. All right. So another activity we're going to talk about, and this would take forever to do, like the red chips thing. Okay, in this activity, you will use a population of quantitative data to investigate whether a given statistic is an unbiased estimator. So we're going to look at the centers compared to the population, which is the true proportion or the true mean or whatever we're talking about, okay? So in this case, every student is going to write their height down on a piece of paper. We're not really doing this, but pretend like you're writing your height down. I know. All right, and then after your teacher has mixed the bag, so we mix it all up, every single person takes the bag, and everybody grabs 4 cards, and you put them back in the bag before you pass it to the next person. And so you should have 4 heights, right? So n is 4. That's how many you're drawing. You're going to have 4 heights, and you're going to find 2 things. You're going to find the mean of the heights, meaning x bar, right? Mu would be the true mean of every single person in the class, right? But you would find x bar, the mean of the 4 heights. Okay, then we would also find the range. So we would find the range of the whole entire class, right? The tallest person minus the shortest person. And then you would find the range of your sample. So you're going to take 4 people out of the bag. You also find the range. Okay. So we would go put our chart up on the board. So here's an example. Somebody might have these 4 heights that they drew out of the bag. So their sample mean, their average, right, is 67 inches. And the range is the highest minus the lowest. So their range is 13. So every person would do this, and it would take forever to pass the bag around. So that's why we're not doing it. Then you plot 2 different dot plots. All right, we're going to do a dot plot for the mean and a dot plot for the range. Okay. Based on your approximate sampling distributions of X bar and the sample range, which statistic appears to be unbiased and which appears to be biased? So here's the results from someone else's class that did this. Okay. So in this lovely guy, we have a sampling distribution. So however many kids drew out of the hat and took the average of the 4 heights that they drew, n is 4. Sorry, this is hard to read. Okay? And right here they tell us the center mean. So by looking at the graph, our center mean is about 65.67, right? However they figured that out with all these. And our population mean, the true mean, if you took every single person in the class, found the true mean, is 66.97. Are these pretty close? Yes. So is this biased or unbiased? Good. So when we did X bar or average, we got an unbiased result. Okay. So our X bar, which is our sample, is close enough when we did a whole bunch of simple random samples to the true average of the class height. Now this one over here is the range. Okay. So every single person drew 4 heights, and they did the highest minus the lowest, and they put a dot plot up there. So the center, meaning the mean of the ranges. So I know this is weird, right? It's like the mean of the ranges. But when you have a dot plot, you can find the mean by locating the center, right? So even though we're talking about ranges, there is still a mean to the distribution. So the mean of the distribution is about 10. But is that the true population range? No. The true range is always the highest minus the lowest. If you take 4, doesn't it make sense that your range is probably less? Because you're not always going to pick the highest and the lowest. All right? So the true range is 21. So is this biased or unbiased, you guys? This is biased, all right, because they don't match up. They are not similar enough. Make sense? Cool. So the range is pretty much always going to be a biased estimator. Okay. All right, second objective of the day, spread. Low variability is better. Okay. Who watches Survivor? I watch this in college all the time. Okay. Television executives and companies who advertise on TV are interested in how many viewers watch a particular show. According to the Nielsen ratings, Survivor was one of the most watched television shows in the United States during every week that it aired. Suppose the true proportion of U.S. adults who have watched Survivor is P equals 0.37. Okay. True proportion right here, 37% watch Survivor. So then we make a dot plot. So we're going to take 400 simple random samples of size 100. Okay. So I have 100 people, and I ask how many of you watch Survivor, and I do that 400 times. Okay. So, and you find the proportion out of each 100 people that watched Survivor. So we see that the sample of 100 people often gave p hat quite far from the population parameter. So let's look at this. Let's just look at the graphs. Okay. So the first time around that we do this, our sample size is 100, right? So I ask 100 people, how many watch Survivor? And some people are over here where my sample produced only like 26%, but some people over here, my sample, I asked a lot of college kids probably who really liked it. It was like 54%, right? But the center is still in the middle, okay? Both of these are unbiased. Doesn't have anything to do with bias in this little section. They're both centered around the center. We're talking about the sample size. Okay, what if I do another simple random sample, and this time I ask 1,000 people, and I do it 400 times, and I find out the proportion of 1,000 people that watch Survivor. What is the difference in the spread? This guy right here has less variability, right? Less of it. That's better, okay? Less spread is better. So bigger sample sizes, is that better? Yes. The more people you ask, the less variability. So that's the next thing you're going to write down. Larger random samples give us more precise estimates than smaller random samples. This has nothing to do with bias. Okay? Bias, we're looking at the center. And another way we say this is the variability. You might want to write down that word. The variability of a statistic is described by the spread of its sampling distribution. This spread is determined mainly by the size of the random sample. So whether I talk to 100 people 400 times or 1,000 people 400 times. Larger samples give smaller spreads. The spread of the sampling distribution does not depend much on the size of the population. Okay? So if I am talking about Devlin as my population versus Cherry Creek, which is like huge, right? For my population, doesn't matter as long as the 10% rule applies, which we'll talk more about. That's the n is less than or equal to 1/10 of n that we did. Okay. So let's see if we understand the centers and the spreads. So the histogram above left, so this guy right here, shows the intervals in minutes between eruptions of Old Faithful Geyser for 222 recorded eruptions during a particular month. For this population, the median is 75 minutes. So this is the population. It's every single eruption for the month. So we're saying population right here. Okay? And its median is 75. So then we use Fathom software to take 500 simple random samples of size 10, okay, from the population. So 10 of those, 222, and you calculated the time in between and found the median. So the 500 values of the sample median are displayed in the histogram above right. So this is our sampling distribution. Notice it's a bar graph. That's okay. We're still talking about a whole bunch of samples instead of one thing. Okay, which is the distribution of the sample that we learned yesterday. All right, so in that 500 that we took, the median is 73.5. Is the sample median an unbiased estimator of the population median? What do you guys think? Okay, the correct answer is no. The mean of the approximate sampling distribution of the sample median is not equal to the true population, okay? So again, they will be very, very close, like almost exactly the same, and then you can say that it is unbiased. So this would be biased. All right. Suppose we take in samples of size 20 instead of size 10. All right, so we have a sampling distribution. That was the second graph. And we did samples of 10. Now we're increasing our sample size, just like the survivor example. Would the spread of the sampling distribution be larger, smaller, or the same? So I'm increasing my sample size. What happens to the spread? Smaller. Okay, larger samples provide more precise estimates because larger samples include more information about the population distribution. All right, describe the shape of the sampling distribution. So let's look at it. This is the sampling distribution. What's the shape, you guys? Skewed left. Good. Unimodal. All right. So there you go. Any questions?